Hi there, my name is Logan Thomas, and this is For the Win's team presentation. For centuries, exploration of other worlds has been a curiosity to humans. What else lies out there for us to discover? Could there be life on Mars? Could there be the basic building blocks of life somewhere else out there in the solar system other than our pale blue Earth? Recently, focus has shifted towards the outer solar system and the moons of Saturn. Of the 62 moons of Saturn, the largest is also the most interesting one.
Titan.
On January 14, 2005, the European Space Agency's Huygens probe descended through the dense atmosphere that has drawn interest from scientists and astronomers for decades, transmitting back enough substantial data to solidify Titan's place in the future of human space exploration. Titan is the only known natural satellite in the solar system, with a thick atmosphere whose composition of nitrogen and methane create an abundance of complex hydrocarbons and other organic chemicals. Only 1/7 of Earth's gravity and over 700% higher air density at cruise altitude, a mission utilizing an unmanned aerial probe is destined for the moon's future exploration.
So to tackle this project, our team split into an aerodynamics team to focus on the wing, fuselage, and tail design, a propulsion team to focus on power supply and propulsion, a structures team to focus on the structural system, material, and deployment procedures, and an avionics team to focus on the scientific payload, navigation and control system, and overall mission design. To assist these sub-teams, we also had a CAD specialist modeling the designs, a configurator to integrate the designs from the sub-teams into the flyer, and a capture manager handling the logistics of the team. To fulfill these requirements, our team came up with several ideas. Propulsion decided on using radioisotope thermoelectric generators to power the flyer indefinitely. Aero looked for high-efficiency airfoils to develop the wing before focusing on the fuselage to hold the payload. Both Aero and Propulsion worked together to come up with a design that would be able to fly the 25-kilogram payload. Structures initially focused on materials that would survive the extreme conditions on Titan, and eventually worked with Aero to design a system to fit the flyer into an entry pod. Avionics looked into the electronics of finding instruments that could be used for the scientific payload. Since the plane was going to deploy from an entry pod, we also decided that this would be a great time to deploy whatever lander we bring with us to reduce weight and complexity from an additional plane-based deployment system. I'll let the rest of the team go more in depth on the design.
After graphing Reynolds number based on the select flight regime and various chord lengths, a two-dimensional analysis was undertaken in Xfoil in conjunction with the Reynolds number plot. In this airfoil study, 47 designs were tested, and each one was judged based on figures of merit. On a range of -5 to +10 degrees angle of attack, the figures of merit included max lift-to-drag ratio for descent and climb conditions, low moment coefficient for flexibility with tail sizing, and most importantly, minimal drag. From this analysis, the list was narrowed to 5 airfoils for their high lift-to-drag ratios. Ultimately, the Epler 420 was chosen for the best combination of high lift-to-drag ratio in descent, climb, and level conditions, and its small drag coefficient. After evaluating the environment of Titan, it was concluded that airspeeds must be kept low to avoid excessive high Reynolds number and drag. This eliminated lifting bodies from the analysis altogether. The remaining major configurations considered were the conventional tube and wing aircraft, the twin boom, and the flying wing. Each configuration featured both attractive and unattractive characteristics. For instance, the conventional configuration is simpler to build and analyze, and on the other hand, nose-mounted engines can cause noise in the instruments. The twin boom boasts of a pusher-prop capability, while the prop wash can lead to vibration in some cases. Finally, the flying wing features a lower drag profile due to less surfacing, however, stability suffers from not having all control surfaces available. In the end, the twin boom configuration was chosen on account of possessing the potential for more convenient packing methods and less surface area. The first step in the downselect process for the flyer design was the wing. All of the analysis for this process was done in XFLR5, starting with the Hershey bar. This wing set baseline numbers for the lift coefficient, induced drag, lift distribution, and so on. From there, Different aspects of a wing were tested separately to see the effects on lift. For example, both positive and negative sweep were tested and proved detrimental to overall lift. And twist seemed to improve the coefficient of lift, but negatively affected the lift distribution. The next phase of testing proved that adding dihedral to the wing positively affected the lift-to-drag ratio, induced drag, and lift curve. Now, for fuselage design, several factors contributed to its final design. Being in the later stages of analysis, available space and drag became a mounting issue. In terms of the drag buildup, it was imperative to conserve surface area while accommodating as much room as possible for the rather large power plant and accompanying payload. Designs were made in SolidWorks, where a surface area value was taken and put into a drag buildup worksheet in Excel. Preliminary designs tested simple concepts like an ellipse, a slotted oval, an ice cream cone, and a streamlined body. All of these concepts could not provide enough room without adding overwhelming skin friction drag. From there, a parabolic nose and a blunt end for the propellers were given to the slotted oval for a more optimized design. This bullet fuselage was iterated 3 times to reduce surface area and provide sufficient space for instruments. However, this design just did not possess efficient use of space and desired drag reduction. Therefore, collaborative efforts among team members produced a contoured fuselage which excelled in drag reduction, space for instruments, and space within the capsule. For tail design, packing efficiency was the main design motivation. With a fuselage length of 2.82 meters, not much room could be left for conventional empennage. In that case, with additional control advantages, an inverted U-tail was chosen. Sizing the tail came by assuming a NACA 0009 airfoil and inputting appropriate geometric and aerodynamic parameters into the given tail sizing worksheet in Excel. For the analysis, the vertical stabilizer was assumed to be the vertical components of the bent sections that were angled at 60 degrees from the horizontal axis, and the horizontal stabilizer was assumed to be the straight section of the tail plus the remaining horizontal component of the bent section of the tail. To another Excel spreadsheet provided by Professor Jacob, the stability margin and several stability coefficients were calculated from predetermined and designed values. From the analysis, the static margin is about 0.239, and the other values indicate stability in level and steady flight conditions.
Due to Titan's extreme thermal environment and dense, hazy atmosphere, a radioisotope power source is optimal to both generate enough heat to maintain a stable internal temperature for electronics, as well as enough energy to power them. Jet Propulsion Laboratory and Aerojet Rocketdyne devised the Segmented Thermoelectric Modular Radioisotope Thermoelectric Generator, or STEM-RTG, system as a potential follow-up to the multi-mission RTG currently in use on the Mars Curiosity rover. With its 17-year lifespan and 489-watt power output at a mass and diameter within our original design estimate, the 18-block model was an obvious choice, although a similar lower output realization of the design could also be employed with minimal impact to the flyer's operational capabilities.
Our ideal motor would be brushless. The reason we want a brushless motor compared to another motor is they are more reliable and efficient. It would operate at 230 RPMs and have a torque of approximately 11.58 Newton meters. It would also have an efficiency of 90%. I will discuss how we arrived at those numbers in a second. We found a similar motor to these specifications on Hacker Motors' website called the A3052S UAV. This motor is lightweight, has an input power of 250 watts, and is over 90% efficient and operates at 680 RPMs. This motor is shown to the right. Since we found a similar motor online, we can assume our ideal motor is within reason. We were able to calculate the best RPM our motor would operate as well as the best diameter blade for the best efficiency. The highlighted portion results in the best conditions for a UAV. We used the J and CP values to determine the best efficiency using the graph to the right. Operating at these conditions I listed above are propellers that would operate at an efficiency of approximately 87% from 2 kilometers to 8 kilometers in altitude at a prop angle of 52.5 degrees and a diameter of 1.25 meters.
For structures, we decided to go with a dual spar system consisting of a tubular spar close to the leading edge and an I-beam spar close to the trailing edge. The tubular spar will be the main spar because its ring cross-section will distribute the forces felt by the wing instead of concentrating them into the roots. The tubular spar is to be made with 3 layers, and the internal layer will be a copper UNSC 11000, also known as electrolytic tough pitch copper. This is to help transmit the heat created by the power source through the wings to another layer of copper that will be on the leading edge of the wing to prevent icing. Around the copper in the tube is carbon foam. This was chosen because it works very well in very high temperatures. The exterior layer of the spar is to be Nomex honeycomb sandwich composite made by DuPont, which is lightweight but strong, exactly what is needed for this application. The honeycomb structure will also be used for the I-beam spar. The flyer will then have a truss-like structure throughout the ribs that will be made of carbon fiber. This was designed to withstand the aerodynamic forces of flight we will be experiencing while flying on Titan. The skin on the aircraft is to be made of a self-healing carbon-based material, shown to the right on the screen. Since this material is thermally conductive, it will help keep the exterior of the plane warm. This self-healing material is also useful for the internal core of the structure, since fractures can be repaired automatically. A huge factor in utilizing this material is because this makes our aircraft less prone to failing. Therefore, any microcracks formed from the cryogenic temperatures can be repaired by the built-in self-healing properties. The fuselage has a ring-frame structure supported by longerons and a self-healing composite skin. The bulkheads, booms, and tail are made of Nomex honeycomb composite. The tail can be solid to allow the static margin to be adjusted based on the chosen payload. Overall, we can design for a load factor of 3.
To fit inside the entry pod, the plane was designed to have folding wings and a sliding twin boom tail. The wings were designed to fold down so that lift generated would keep the wings in place as opposed to trying to collapse them. To compensate for the cut in the structure, 2 cryogenic titanium springs will trigger once the wing is completely deployed and push a pair of titanium pins through a channel connecting the wing pieces, locking the wings in place. To reduce failure, magnets can be placed on the inner surface to help align the wing pieces. Once deployed, the self-healing skin can activate and seal any cut in the first place, further strengthening it. A similar method would be in place for the booms, which would slide back until a notch in the tubes line up with another set of spring-loaded pins locking them in place. The overall weight of the flyer can be broken down into 4 major sections: the structure, further broken down into fuselage, wing, and empennage, the scientific payload, the STEM RTG, and the avionics equipment. The overall structure is designed to take up a quarter of the overall mass to handle extreme loadings that the flyer could experience. Total, the flyer weighs 186 newtons on Titan, or 138 kilograms. Drop payload situations aside, this weight is not expected to change.
The Flyer's electronic suite will contain all the instrumentation needed to safely navigate, communicate, and collect data with the onboard scientific payload. The avionics components on board include a triple redundant autopilot controller, altimeter, inertial measurement unit, small deep space transponder, command and data handling computer, and a host of sensors to monitor airspeed, horizon orientation, and current atmospheric conditions. Ideally, to communicate with Earth, the flyer would be accompanied by a relay satellite such as Mars Odyssey or Reconnaissance Orbiter, and use an ultra-high frequency antenna to relay data to the Deep Space Network. However, depending on mission requirements, the flyer could be outfitted with a long-range antenna to communicate directly with Earth. The suite is designed to offer a flexible and versatile environment for a range of potential scientific instruments, including mounting for downward-facing imaging equipment, controllable ventilation to allow active atmospheric sampling without direct exposure to Titan's extreme temperatures, and an integrated control system to manage instruments as well as store and relay data. In addition to instruments in the electronic suite, the flyer is also capable of carrying a deployable payload on the underside of the fuselage, which can be accurately deployed at a target site such as ice hydrocarbon dunes or specific liquid bodies of interest.
Utilizing the power available from the STEM RTG,
The performance range of the aircraft has drastically increased from the previous power source used. Even though the aircraft is designed to operate at an altitude of 8 kilometers, it is able to operate in a wide range of altitudes from Titan service to well above 40 kilometers.